Hello, everybody. Today, we're going to continue our conversation on chemical kinetics by focusing in on actual measurements of chemical rates. So, one of the first things we have to think about is the actual physical apparatus that we're going to need to try and measure chemical rates. And so, most of these arrangements are going to fall under one of three major categories. The first is the one you're probably the most familiar with. So this is called real-time analysis. So this is your good old-fashioned, I set up a beaker of solution and I actively monitor the concentration over time. So this is often done with something like a UV vis spectra. And then you'll either monitor the concentration of reactants decreasing or products increasing as you let the reaction occur. But this does give us a certain degree of limitation in how we're actually watching the concentrations move with respect to time, and often requires rather slow reactions or um, and systems that work in very well behaved and well mixed arrangements. Another modification of this is what's called a flow method. So these are also fairly common, and these are nice because they're easier to set up in more of an automated arrangement. So in flow method analysis, the general idea is you'll actually be able to combine your two reactant chemicals inside a mixing chamber and then let it move through some sort of straight tubing where it can move past the spectrometer. Now, what's very nice about this arrangement is that you can usually move the spectrometer along the reaction path. And so what you can do is see how the concentration, how the rate changes at various different physical points. However, if you know the flow rate of the material, each of these physical points um, is related to a time after reaction. And so by adjusting the flow rates, the mixing conditions, and the position of the spectrometer, you can actually gain a lot of information about the chemical reaction. And this is also highly beneficial is that you can just simply allow the reaction to continue and get much more of an averaged uh, signal for the absorption at that given point. And so you're less constrained by the randomness that may be inherent in trying to do a real-time analysis where you start wondering, is this typical or atypical? And then you need to do multiple reactions to confirm. So it can be a very good alternative with some major advantages. However, you may notice that these two methods essentially both rely on some sort of real-time analysis. So again, if you have a photoabsorbing chemical, which you can monitor with a UV vis spectra, that's great. However, if you're dealing with a spectra with a little bit uh, longer acquisition time, say a mass spec, an NMR, or even an infrared IR in order to monitor your species, well, neither of these methods work too well. And so in this case, what we often rely on is what's called quenching methods. So this is where you say have a real-time analysis, I mix up a beaker, and then I either stop the reaction in the beaker or I remove a small sub quantity of my reaction and put it in another container where I've then stopped the reaction. So then the question becomes, how do you stop the reactions? Well, this can either be done chemically by, say, if I have a peroxide catalyzed reaction, I can put in an antioxidant to consume all my peroxides. Or you can try and physically stop the reaction. This is most commonly occurs through rapid cooling of the system. Because as we'll see later, as the temperature drops, all of our rates tend to drop as well. And so you'll often see these used quite commonly in the literature. And again, one of the biggest benefits is that it allows for a more thorough analysis of the chemical mixture at each and every point of time, especially if you have a species that isn't conducive to UV vis spectrometry. So now that we have an idea of how we're collecting measurements, and we now have our chemical reaction from last time, now how can I try and use these experimental tricks to try and actually back out my rate of reaction? So, one of the first things we can do is what's called a isolation method. So let's say I have a reaction where I have both A and B as reactants. Well, I'm not sure how much A is dominating the rate of reaction versus how much B is dominating the rate of reaction. Because as we saw with our generic rate equation, ideally, if this is an elementary reaction, both should come into play. But it can be a bit tricky to try and analyze it all together. So our major approach is going to be we start by assuming by loading the system with way too much B. And if I do this where I superload the system with B, then no matter how much the reaction proceeds, my concentration of B hasn't really changed. And at that point, I can now treat the concentration of B and its related coefficient as constant. Well, if I do that, I can just bundle it up in with my rate constant. And so now instead of using the true rate constant, we'll use an effective rate constant. In this case, we'll call it K prime for reasons you'll see in a little bit, where our K prime is going to be related to the real rate constant times the uh, concentration of B to the order of the reaction. And again, that's exactly where these methods really come into play, is because by monitoring the concentration, uh, how the concentration of A varies with the rate of reaction, I get the order of the reaction or the effective number of molecules of A that play into the rate. And these are the same orders of reaction that you often see in general chemistry. And by making sure that B is at a much higher concentration, it lets me first isolate the uh, order of A, and then it lets me come back and say, well, if I collect multiple, uh, if I collect my K prime, and then I change my concentration of B, I should be able to collect another K prime and then another. And by monitoring multiple K primes and multiple Bs, you should be able to back out the order of the reaction with respect to B and the overall or real rate constant of the reaction. However, how we try and do this can also be a little bit tricky. So in practice, another method you can do is what's called the method of initial rates. So we can combine this with the isolation method. So I start with a complicated reaction. So I'm going to superload it with B and then focus just on the order of A. And what we're going to be doing is we're going to assume that if at the very beginning of the reaction, my concentration of A won't have had too much time to change. So the initial rate of the reaction is going to be related to the initial concentration of A present in solution. And again, this will be related to an effective rate constant. So ideally, our effective rate constant should be our real rate constant, but sometimes there may be other factors that will cause the rate constant to change with respect to time as other species build up in solution. So ideally, this should be our real rate constant, but we do have to acknowledge that it may not be. But by doing this, we should still be able to back out the order of the reaction with respect to A. And one way we can do this is, as physical chemists love to do, try and linearize it into a equation that's more easy to graph. So one of the ways we can do this is by taking the log of the reaction. So if I do this, what I can do is plot the log of my initial rate versus the log of my initial concentration. So as I vary my initial concentration, I can get a change in my initial rate. And then we can go ahead and plot this initial concentration versus initial rate. And what ends up popping out is that our slope will end up being the order of the reaction, and our intercept at 0, which is going to be somewhere over here, what we'll end up finding is that our intercept will be related to the log of the effective rate constant. So this is a good way to try and back out our rate constant and our order of reaction in a fairly simple approach. And this general method and style can also be applied to other systems, such as if I am using the isolation method as well. I have What I've done is I've obtained multiple of my effective rate constants, or our KR primes. And then by plotting these versus our concentration of our other species, our species in excess, so B, I can back out the order of the reaction with respect to B, and again, the total rate constant. So again, this is a fairly general strategy that can be really helpful. So what we're going to do next time is try and talk a little bit more about orders of reaction and how we can determine simple orders of reaction with slightly simpler techniques and what information they can provide us. So until then, take care.